before I forget.
Cool, good.
Cool, and we're off. Yeah, so today the main topic is Hamid Faruqi. I'm hoping I said your name mostly right. Is going to be presenting on the PyMFR package. So whenever you're ready, feel free to take it away.
Hey, 1 second, let me share my screen. Can you guys hear me?
Yep.
Okay.
Loud and clear.
Yeah, I prepared these slides. So yeah, my name is Hamid Faruqi. I'm a applied physics PhD student at NJIT, or I just started. Although I still think of myself more as a programmer. I started programming when I started middle school like 10 years ago, mostly in game modding and game development. Then during my CS degree, I graduated this spring in computer science. I got into heliophysics research. So now I'm doing a physics PhD, but I'm not really much of a physicist, at least not yet. I still think of myself more as a programmer. So here I basically made a more efficient implementation of physics-based methodology for detecting magnetic flux slopes in the solar wind. So my actual implementation is not that there's not that much to it. So most of this presentation is about the significance of it and comparing it to the existing implementation. So first of all, magnetic flux slopes in general. Originally, they were observed in 1980s as so-called magnetic clouds. Nowadays, they're accepted to be the internal structure of ICMEs, which everyone knows is the most important thing in space weather, basically. Besides being in ICMEs, though, magnetic flux slopes are also regularly observed in the solar wind, like around 10 every day at Earth, and but these ones are much smaller. The common magnetic flux slopes are called small-scale magnetic flux slopes, and instead of tens of hours, they only last tens of minutes usually. So this is a picture of what the solar wind looks like according to a common hypothesis. So many believe that the solar wind is composed of a bunch of flux tubes, which are like distinct regions of plasma with their own orientations and their own stuff going on inside of them. So recently, there was the development of an automated detection algorithm, which found a large number of small-scale magnetic flux slopes, which kind of shows that many of these flux tubes, if not all of them, are probably magnetic flux slopes, which mean that they're not just tubes of distinct plasma, but they also have some twist to them. A big question about them, though, is where they come from and how they form. So a lot of people think that they come from the sun. Others argue they come from the turbulence in the solar wind. And nowadays, some people say that they probably come from both, like at 1 AU, maybe more of them are from the turbulence, whereas closer to the sun at PSP, maybe more of them are from the sun directly. So the classical model of a flux slope is this Lundquist model. I put a code for the Lundquist model in my on the PyMFR in one of the demos. So it's just this simple twisted magnetic field. This is the magnetic field and from looking from a cross section in 2D. And here's what it looks like if a spacecraft goes through it. So the axial component, which goes through the magnetic flux slope, the Z or blue over here, that one goes up towards the center and then goes back down. The vertical component crosses the x-axis. It goes from negative to positive or positive to negative, depending on if it's right-handed or left-handed. And the axis along the spacecraft path, the x-axis, kind of stays the same mostly. It could change a bit depending on the structure, but usually it doesn't change as much as the other ones. So in order to actually study magnetic flux slopes, we usually only have a single spacecraft of data. So even though it's a 3D structure, we only have a single line going through it, essentially a spacecraft passing through it in a line. So you could usually approximate a flux slope structure as 2D at a local scale, even though it has some larger shape on a local scale. You could approximate the part that the spacecraft passes through as a cylinder, and then you can take a circular cross section. But the problem is you need to know the orientation of the cross section, and you need to know the direction it's moving, because it might not be moving exactly in the same way as the solar wind plasma. So often it's assumed that it is moving the same way as solar wind plasma, and it is moving or it's moving straight radially from the sun. And as for the orientation, a common technique is using minimum variance analysis. So that's based on the fact that the most changing axis is usually the vertical axis of the cross section, which goes from negative to positive, and the least changing is usually the x-axis, which is the spacecraft path, and the intermediate one is the axial component. So usually then they could use the minimum variance analysis in lots of modeling papers. But the problem with minimum variance analysis is that depending on whether the spacecraft actually passes through the center of a flux slope or at the edge, which axis changes the most could vary a lot, and sometimes none of them could be the correct axis. Minimum variance analysis essentially builds a matrix of the variance of the magnetic field, and then they find the eigenvectors of the variance matrix, and in order to find the least and most and intermediate variance directions, but they're not necessarily the flux slope axis. As for the velocity of the flux slope or the frame, besides assuming that it's the same as the plasma velocity, a more sophisticated way is to use the de Hoffmann-Teller analysis, which is essentially using least squares from linear algebra in order to find inertial frame where the electric field is zero. So using electromagnetics theory, if the electric field is zero, then the magnetic field has to be time static in that inertial frame, or meaning if you're moving at that speed, then the magnetic field would appear to be not changing in time. Then so it's a sufficient but not necessary condition, basically. Like the electric field could be not zero, but the magnetic field could still be not changing. But if the if the electric field is zero, then that means that the magnetic field is not changing. So, but on the other hand, usually in the solar wind, you can find the Hoffmann-Teller frame where the electric field is zero. So that's used in the GS methodology, which is what PyMFR's detection methodology is based on. So based on the GS equation, Chang-Hu and Sonarp in 2001 developed this GS reconstruction methodology. So it's basically uses the GS equation, which is this thing right here. It's based on the assumption that the magnetic field, or basically it's the assumption that everything is 2D. So all of the quantities don't vary along a certain axis, basically. Even though it's in a 3D space, a certain axis, nothing changes along that axis. So in this case, the axial direction, the z-axis of the flux slope. Under this assumption, and also assuming that it's an magnetohydrostatic equilibrium, so the pressure is balanced with the magnetic field strength, then this GS equation can be used. And if this GS equation can be used, then if you can find the axis orientation of the flux slope and the propagation direction, and the propagation direction, they use the de Hoffmann-Teller analysis from the previous slide, and they have some methodology for the axis orientation, which I'll show on the next slide. So if you have those two pieces of information, and you also have measurements of the spacecraft path, then you can use this GS equation to numerically solve for the whole 2D cross-section. So they can use this to reconstruct the shape of the overall flux slope, even though they only have a single line through it. So then they get something like this image, which is just based on numerically solving this differential equation. As for finding the axis, they introduced this methodology based on the GS equation. So through the derivation of the GS equation, one can realize that the magnetic vector potential, which is essentially just the integral of in this case, it's just the integral of the y component of the magnetic field, or the vertical component, assuming a certain flux slope orientation, should be the same at every magnetic field line along the flux slope structure. And furthermore, certain other properties, such as the magnetic field along the axis, and the plasma pressure should be the same at every magnetic field line. So since we have a scalar A, which is already known to be the same, and we have these other quantities that are also the same, you should be able to make this plot here, which has as the x-axis A, which is a function of the magnetic field line that it's on, and also the y-axis is this transverse pressure, which is just the summation of the gas pressure and the magnetic pressure, which should along the axis. So both of those should be the same for every value of A, because they're all the same on the same magnetic field line. And that way the sum should also be the same. So they make this plot, and they do this for every possible axis orientation out of a set of guess axes, basically. So they try all the different axes in or different orientation directions that are possible, basically, within like a certain grid of space points. But if it's the correct axis, then these two lines should be the same, because the first line is the first half of the spacecraft path through the flux rope, and then they divide it into two parts. And then the second part, if it's if the transverse pressure is a function of A, which is then it'll this second line or going back down should be the same as the first one. So essentially, you should have the same value at every magnetic field line. That's what this is saying. So they try all the different ones until they find the axis that these two lines match up the best. So then that was in 2001 and 2002 they developed that. So that was a couple of decades ago now. But a few years ago, they developed this automated detection algorithm, which uses the same double folding pattern that they use to find the axis orientation, but they also use that as a criteria now to determine if it's a flux rope. So first, for a certain time window, for a certain axis orientation, if this matches really well, then that's their criteria for finding flux rope. But the problem with that is you need to do this very, very exhaustive search for every single time window length, for every single starting time, for every axis orientation. This is in total around 100 something axis orientation. This is a very large number of starting times for 21 years of data that they did their study on, and large number of different window lengths or different possible durations of the flux rope measurement. Then they check for every single one of those if it's a flux rope using their calculations. And then they apply some filtering process at the end to determine the best candidates for the flux ropes. And then they've used that to make their catalog. And this is a flow chart they have showing the process. So PyMFR, basically I developed it quickly in the end of the summer. I basically implemented their algorithm, but instead of using a direct implementation like this, I used vectorized like array computations and using PyTorch. So instead of directly doing this loop, I generate all the data that it checks inside of the loop for all the different axis orientations for a certain batch of time windows, and process them all at once using the GPU. And that way it's much faster. So in the original paper, when they did this way, they had two universities using computer clusters to do it. But in my implementation, essentially the difference is that it's much faster because it uses the vectorized computations, and I was able to run it in like less than a minute on a day's worth of data. So it's that's just on my laptop. So it's a big performance improvement. So here's an example of the results on the collab that I have linked on the GitHub. So here you can see this one ran in just 20 minutes using a day's worth of PSP data, and it finds the same exact two flux ropes that they have on their website for that day. And next, what I want to do with PyMFR is, first of all, clean up the code. I've been in a rush at the end of the summer before I started my PhD classes, so it doesn't have unit testing or anything. And it also could use some more documentation and such. And besides that, I thought I'll probably add some other features to it instead of just this algorithm implementation. So I want to include other tools useful for studying magnetic flux ropes and in situ data, like fitting the data to models and like the Lundquist model and other models, and also the GS reconstruction where you generate the whole 2D map from the observations. You could see this link, and you can go to the GitHub if you want to see the code and how it works. And if you happen to be interested in using it for some study, you could email me and I could help you with it. That's all. Thank you.
Thanks. Any questions from the crowd here?
Yeah, awesome. Good job on the speed boost up there. That's a huge difference. I was wondering, I mean, obviously you were just comparing it to that other implementation there. Did they have a Python implementation of this, or
No, I think
was
it's in
there a
MATLAB.
MATLAB? That's what they were in.
It's not open source, so that's also the other advantage of mine is that it's open source. No one has access to their implementation, so you can't do it without them working with you, I guess. But their implementation is closed source, so I don't actually know for sure if it's MATLAB. I do know they have the reconstruction code on GitHub and MATLAB, but that code is unmaintained and like decades old.
Oh man,
So you
nice.
say you've open sourced this. Did you get this through tech transfer?
Sorry, what?
You say you open source this. Did you get this through your university's tech transfer?
No, I just put on GitHub over here.
Okay, so that means they could come in and claim it.
Can they?
Yeah.
How so?
Depends on exactly what you signed when you started there. This is a big problem that we've got, is that the vast majority of us work for universities or research institutions that lay claim to all of our intellectual output, regardless of when we did it.
So
Interesting.
I can jump in on that a little bit.
Thanks, John.
If the money that was used to generate this was on a grant or contract that says in there, all code will be made open source, then your institution already made the decision to open source it. And the IP, the tech transfer people, at least at APL, they look at that and go, oh, we already decided we're giving this open source. So go to the public release people, but intellectual property wise, as long as we just know that it's there, you've already, the grant says you were going to open source it. So putting that language, even one sentence in the grant, all code on this and data and everything on this project will be open source, that short circuits a lot of the legal discussion. If it's not in there, then John's right. You have to go through some process to get them to release it, because they're going to say, oh, we could make money off of this. Yeah, that's at least what happens at APL.
Yeah, it's not true. They probably can't, but
Well, they will want to look at that.
yeah.
Yeah, and then it takes 3 months to convince them no.
Oh well,
Interesting.
they're fast. Los Alamos, it takes a year.
They've
Yeah.
tried to streamline it. We're trying to make it faster. We're trying to make it anyway.
Does that actually happen often?
I don't think we've actually been blindsided by it in the community before, but it is a definite point of potential exposure.
Because my the other professors and the professors who work with me know about this, that I uploaded, but they didn't say anything, so I assumed it was all right. But
Yeah, you probably want to check with them about, and again, if they don't think in software terms, they may not have had the exposure to this. It's just this is something that is part of what we're trying to work out in this community, right? Is that if your output is papers, no university is going to flip out over the fact that you submitted a paper. But for those of us for whom software is part of our output, that's less broadly accepted.
I
Yeah,
see.
it's better to have it officially there so that it never comes back to bite you and you don't ever have to worry about it. But it does take, the first time you're greasing the skids, the next time it's easier.
Yeah, I think John's point of anytime you're having any interaction with a funding agency, if you can get them to put down a requirement that everything you do is open source, that actually helps you.
I see.
Yeah, it
And
sounds
that's
like
coming with NASA. Oh, go ahead. Sorry.
was going to say, sounds like at least worth a conversation with the professor. And please do like post in Slack or something if you get an answer about whether or not this was open sourced by default. If this happens enough times, I'm thinking about even adding something to our like PyHC standards in the open source section about ways to like handle university issues.
Yeah, if we could get resources, that would be great. I'm trying to think. Speaking to your professor might help, but also, gosh, I'll go digging. I know that we know somebody at NJIT that does a lot of code. So that might also be a good person to talk to. I will attempt to go digging and see if I can remember what I'm thinking about and get you their contact info.
I mean, there's a lot of people at NJT who do a lot of code, so
Yeah, that
Yeah,
shouldn't be
but
hard.
in this context specifically, but yeah, if you can think of somebody, go for it.
I had a question about some of the internals, the way you're grabbing the data.
yeah,
The interface that you're using to get it from C to web.
yeah,
Of course, I've worked with this project that uses a different mechanism than their sort of default one that uses a thing called Happy. So I was just going to mention that that call cdos.getData.
yeah.
Yeah, there's some of us have been working on a universal access mechanism that C2Web now also implements. And then if you wanted data from a different place that also had it available with Happy, you wouldn't have to change anything.
I see.
We were just at LASP talking to people a few weeks ago, and one of the LASP people, Jenny, I forget what was her last name. Anyway.
Knuth? Sean, do you know how it's pronounced?
It's Knuth with a hard K.
Anyway, she'd been using Happy, and it was she was very thrilled with it for that reason. Hey, once we got Happy access, then it's available everywhere. And the idea meeting this morning, Happy came up all over the place. People are talking about using it, so that's great. It's probably very similar to what they have already, but it's just a it's not a one-off. A lot of it's designed to be same at different data centers.
And I put a link to it in the chat.
I'll get off my soapbox now.
Yeah. Thanks, Andy and John. 100% agree.
Any other questions, comments from the crowd? No?
I guess I'll just comment.
I have one more question.
Oh,
Yeah, no,
okay, go ahead.
please.
So
Question.
this was funded through a HDEE grant, or this was just something you worked on a different grant, or what was the funding source for this?
I was undergraduate research assistant mostly, although in the summer it was kind of complicated. I'm not sure I was actually officially under any grant at the end of the summer. So at the end of the summer, I wasn't really, the last few weeks of August when I was mostly working on this, I don't think I actually had any funding officially. But over most of the summer I had funding for like some other project and two other projects, but this wasn't either of them.
Well, shucks, if you weren't getting paid and weren't under an employment contract, you might be in good shape in terms of being able to open source it.
But I definitely did a lot of like some of the work, because this wasn't like I just kind of put together stuff that I already had in mind from working on the main projects I was working on for the past since 2021, but I've had like several different funding sources for that from different NSF and NASA grants.
This is entirely a side project that you did only on the weekend and you never thought about it at work.
That's what I heard him say.
No, I did.
That is absolutely what I heard.
I did present it and stuff at work, but like.
No, we were just trying to goof around with you for the open source thing.
Okay, I think we are going to use it for our research and stuff, but I didn't like make this as part of like the main thing for any grant or anything like that.
Seriously though, that could be enough to make the case that it should be open if you actually volunteered your time.
Yeah, particularly as an undergraduate.
Now at APL, the intellectual property agreement you sign when you come here, it claims your free time activities too. I've known people that did not apply because of that, actually.
We have a lot of other open source code too, but those are mostly associated with papers, like because there's a lot of interaction between certain people for the computer science department, like a lot of CS students and PhD students, and me when I was an undergraduate CS student, and some CS professors. So they do like machine learning and also like simulation stuff with the physics department. So there's quite a few NGIT open source repositories for this heliophysics stuff. They have like solar flare prediction,
Right.
IC prediction, stuff like that.
No, that's a big activity at NGIT, right?
Yeah.
Yeah, so let me see here. I was just popping through our PyHC projects page, and it doesn't look like we've added you as a PyHC package yet. I absolutely think this does belong under our PyHC
100%.
umbrella. I mean, yeah,
100%.
this is a functionality that I'm not seeing in any other Python packages, certainly none that we have, and huge speed improvement over what the current technology is. So I want to snatch you up quick. Do you happen to know what the process is for like opening a PR on our website to like add your project and stuff?
No, I don't know. I mean,
Yeah,
I know how to do pull requests in general though, so.
Yeah, I couldn't remember if we had pointed you to that before or not.
I mean, I've done millions of pull requests. I mean, not millions, like a lot. But before, especially before college, I used to do a lot of GitHub stuff.
Yeah, really the only formal process we have for like joining PyHC, quote unquote, is really just getting you up on the website. And I can point you to like, we have a link somewhere with instructions, but it's basically just like adding some metadata about your project to a YAML file. Like what's the name of it? What's the links to the documentation and the code and all the good stuff. We have some development standards that we encourage every package to, hold itself to. We haven't done any strict enforcing of them yet. So if there's certain parts of these standards that you're not, totally meeting yet, we can work with you.
Yeah, I think honesty is more important on that than anything else, right?
Yeah.
And path forward. I forget. Do we have an HDE call coming up? Because is it kind of on a more of a rolling basis now?
Yes.
Yeah, that sounds right.
Yeah,
Okay.
the HDEE and the HTM, heliophysics tools and
Yeah.
methods, those are both open.
Because this sounds like something where it would make a whole lot of sense to get a little bit of funding for. Because I'm just going to hazard a guess, based on what you said, there's not unit testing and documentation and such. There's quite a bit of work that's going to need to be done to make this really easily usable.
I wouldn't say that. Like in terms of being easily usable, this code is all just for downloading data. All you actually do to use it is just
well, but for somebody who's completely unfamiliar with it, right?
yeah, I mean, if you know the data well, then it's easy. But if you don't, if you're familiar with solar wind data, this is trivial. Like you just download the magnetic field, velocity, density, and gas pressure data, and you just stick in this function and you get a data frame. But if you don't know this data, that might be hard.
Right, but there's stuff. Okay, how does it deal with gaps, that kind of thing? How do you interpret the output? How does somebody else get in and make modifications, that sort of
Yeah.
thing? And you said you have also some ideas for enhancements. I think it's worth kind of slating out. What do you think? Sorry, I don't actually. Can you link the GitHub in
Yeah,
the
the
chat?
GitHub. Okay, I'll put the link in the chat. Yeah.
That lets me be lazy.
The code is not big. Like I have had tens of thousand code repository before, but this one is only like a few hundred lines. So it's not that much code.
Okay, yeah, so you're running on setup tools, and it's just, getting stuff to the point where it's an easy drop-in for somebody is work.
Yeah.
And so you've got a couple of advantages there. One is it's, you get the money, and it's time that you can devote to this, assuming you want to continue to be devoting time to software. And that also means that is something where you put on there, this is an existing internal research code, right? That then we get, as John Vandegrift was mentioning earlier, if you run that proposal through and your grants folks at NGIT sign off on it, that means they're agreeing to have this open sourced.
I'm not sure if I follow. Sorry.
So if you go and apply to NASA for some funding to do some enhancements here, and you can say this is, an existing tool, it's a research code, and you're going to do this work and this work and this work. In order to get that grant from NASA, the NJIT Sponsor Programs Administration or Grants Management or whatever they call it will have to sign off on that. And that
Okay.
means you are free and clear in terms of any question of whether they can assert the right to take it back.
I see. Okay.
That was a dodge I used for a different piece of code. So I'd really encourage you to do that. You can poke us in the Slack or Discord. A lot of us have done HDE projects of various sorts, and I'm sure there are folks who'd be happy to work with you on it.
What you could do too, as a starting out student, is try to write that proposal and put in another institution or get a collaborator or somebody who's done this before and just fund them for a little bit, but that gives you a connection with another institution that you could build on. And they could help guide you through this part of it.
John is showing my hand.
I mean, pick somebody nearby, a university nearby, you could go visit them, or, Zoom obviates that need a little bit, but yeah, that's a good opportunity. It's not that difficult to win those, and those HDEE grants for something that's really in line with what they're calling for. So.
Yeah, and having gone through that grant process early on in your graduate career helps a lot, because there's nothing quite like hitting your postdoc and suddenly going, oh, now I need to find my own money.
I see. Okay. I didn't know PhD students can get their own grants.
Absolutely. This is a good one to start in on because, like I said, the win rates are pretty good.
I'll send you an email, Hadim, after this that gives you a link to where to find the HDEE grants and such, and also CC you on that, Sean, so you can help them with the process of getting PyMFR onto PyHC.
Okay, thanks.
Yeah, and I was gonna drop 2 links in the chat here really quick. Let me do that. I had them right in front of me. Yeah, our README in our website's GitHub has the add instructions, which boom right there. But really it's on point number 2, it links you to this little project addition instructions document, which is like the big one. Blink. So there's the 2 links you'll care about. And yeah, happy to chat offline through Slack or email or anything if anything's funny or needs clarification.
Okay, thank you.
Thank you.
Awesome. Well, thanks again for the excellent presentation and for the work you put in for this project. It's awesome. Does anyone else have any questions, comments, or other subjects to bring up?
I guess I'll point out, in case someone wasn't watching the chat there a minute ago, we were briefly talking in the chat there about doing a little informal session or a class about how to publish packages to pip and conda and stuff. So maybe stay tuned for that. I'm just thinking off the top of my head, feeling like that's something that we could talk about during the fall meeting. So
yeah, that's what I suggested in the chat.
When is the fall meeting again?
November 7 to 10.
Okay, thanks.
Yeah, I'll work on seeing where we could put that in the agenda. There's definitely still room at the moment. We'll just coordinate to see who can cover that kind of thing.
Thanks.
Yeah.
But yeah, if we don't have anything else on PyMFR, that might be 20 minutes early on the telecon here. Give your time back to folks.
Awesome. Well, it doesn't seem like we have any other big topics right now, so let's go ahead and wrap up. Let me quickly take a look for when our next telecon is. Our next telecon will be on the 17th. Topic TBD, but likely another project presentation. So I will see you all then. And until then, have a great couple weeks.
Yep.
Bye.
Thanks, Julie.